Sridhur. He will tell us about the initial results of the burst. So let's welcome Sridhur.
So, hello all, I am Sridhur, and it is my pleasure to introduce you to the initial results of the very large baseline interferometry capabilities of BURST, Taiwan's new radio telescope. And I'd like to take this opportunity to thank Dr. Stomo, Kayan, Oili, and Chibu, Tetsuya, and Chi, Yapan, and Sujin, and the whole BURST team for their wonderful contribution. And I'd also like to thank the organizers of this meeting for this wonderful opportunity. So this is a brief outline of my talk. I'd like to begin with a brief introduction on fast radio bursts and how the BURST project aims to resolve some of the mysteries about it. And I'd also like to report on our initial VLBA test, and then I'll summarize. So, fast radio bursts, FRBs, are these short duration, typically millisecond radio bursts that come from cosmological distances. And since the initial discovery in 2007, research into understanding FRBs has become one of the most rapidly evolving areas in astronomy. But despite our continual efforts, they continue to remain elusive. And I'd like to bring your attention to these wonderful talks and posters for more information about them. So, some of the questions about FRBs that are unanswered are, what are their progenitors? So what causes them exactly? We don't have the answer. And what is the local environment around these bursts are like? Because we know that the local environment plays a huge role in determining the characteristics of these bursts. But we have no answer for this either. And we also know that these bursts arrive from cosmological distances. So, is it possible for us to use these as an independent cosmological tool? So I'd like to bring your attention to these posters which explore this very question. So, the key to answering all these questions is being able to accurately and precisely localize these FRBs. But we know that typical radio telescopes have poor angular resolutions, and that translates to a poor localization. And we know that previous FRB telescopes, one of the most successful FRB telescopes, SHINE FRB, has an angular resolution of about 7 to 11 arc minutes, and FAST, another most successful FRB telescope, has an angular resolution of 2 to 3 arc minutes, which is nowhere close to the kind of resolution we need to understand these FRBs. And that means that out of the over 600 detected FRBs, only 4% of them are actually localized. But we also know that as we seek to get higher and higher accuracy, our detection rate is also going to go down. So, BURST, the Porcelain Universe Radio Survey Telescope in Taiwan, aims to achieve sub-arc second localization for the first time to precisely localize these FRBs, maybe to their host galaxies. And it aims to do this by conducting a nearly all-sky survey of the sky. And maybe I'll leave it to these talks for more technical details about the project itself. I'd like to focus mainly on the VLBA part. So we aim to achieve this sub-arc second localization by conducting VLBA with both domestic and international outrigger stations. So here is a map of the domestic outrigger stations. So we'll soon explain this a little better. And all the proposed international outrigger stations are here: Japan, India, Thailand, and maybe Canada too. And so here I'd like to report on our initial VLBA test that we conducted with the giant meter wave radio telescope in India. So we observed this particular pulsar, a famous pulsar, and giving us a baseline distance of about 4,798 kilometers, translates roughly to 0.02 arc second. And GMRT observed in a bandwidth of 400 to 500 megahertz, while burst observed in a bandwidth of 400 to 800 megahertz. So one of the motivations for us is to see how the correlation strengths vary for various methods. And we know that when we have two signals, they can be compared to see how similar they are, either over time, the time domain correlation, or in the case of FRBs and pulsars, we need to first de-disperse them. I'll explain this in a bit, and we can see how these signals correlate over frequency, which is known as the spectral domain correlation. So our motivation was to see how the correlation strengths compare between these various methods, and this is the Diane's idea to see if we can use frequency integration to achieve a better signal-to-noise ratio and also to improve sensitivity. So maybe here is a plot of the time domain correlation. The correlation strength is shown here as a function of the time lag for two particular polarizations of this observation. And we see, so this one, the left-hand side is for low lag. We had low lag between the signals. And we see the typical peak at the zero lag, and as we go to higher and higher lags, the signal sort of decays off. And to the right-hand side, we have the same figure, but we introduce an artificial offset here, just to mimic the kind of offset we get from observations from two distant stations. We do see a big shift in this case. So let's move on to the spectral domain correlations. So here is the intensity of this signal as a function of frequency and time for one particular polarization. And we see the characteristic frequency dependent time arrival delay of the signal, which is a characteristic of pulsars and also FRBs. And we need to first de-disperse the signal, that is, we have to correct for this dispersion. And here is the de-dispersed signal, the same signal but corrected for this dispersion and for one polarization. And once we have the de-dispersed signal, we wanted to see how it correlates with itself. So the autocorrelation. And here is a plot of the autocorrelation as a function of time lag. We do see the typical peak in zero time lag, and signal kind of fades off as we offset them in time. So we also wanted to see if there is any dependence on cross polarization. Know that there shouldn't be any, and so this is the same intensity but for two polarizations for the GMRT data. And here are the corresponding de-dispersed signals. So once we have the de-dispersed signals for these two polarizations, we can do spectral domain correlation. And here are the results for that are averaged over all frequency channels. And so this is for the cross correlation strength between the two polarizations without any offset. And then to the right hand side, we have the same figure but with a slight offset that is artificially introduced, sort of to mimic the kind of offset we get from two distant locations. So to summarize, so we did the spectral domain and time domain correlations for GMRT data for this pulsar. So this is a success, and our ongoing works are to extend this and to find a cross correlation between the GMRT and burst data. And for future plans, we would like to collaborate with our other potential collaborators. And we already did it with India, and I also learned fairly recently that we also conducted observation with Canada. So here is a map of all the potential external collaborators: India, Japan, Thailand, and Canada. And maybe I'll stop here. Thank you very much. So very exciting updates are coming, so please stay tuned.
Comments? Questions? So if no, then let's thank Sridhur again.